So now let's talk about Hasse diagrams. So this is basically a good way of visualizing partial orders on finite sets, and probably will be very natural. So it might be what you would write down automatically if you were asked to draw a picture of a partial ordered set. So the basic idea, maybe I won't give a rigorous definition, or maybe I kind of will later, but the idea is to arrange in increasing order and connect comparable elements. But the idea is also to leave out any redundancy, so just to draw the basics. So for example, let's consider the set 1, 2, 3, 4 with partial order less than or equal to. So we draw our elements in increasing order. And then we draw an edge between them if they are comparable and the top one is greater than or equal to the bottom one. So 2 is, 1 is less than or equal to 2, so we draw this edge. And 2 is less than or equal to 3. 1 is also less than or equal to 3, but we don't need to draw this edge because we already have these two edges that tell us by transitivity that 1 is less than or equal to 3. So we can leave that out. And similarly, 3 is less than or equal to 4, so we draw this edge. And we don't need to draw this edge because it's given to us by transitivity, and similarly, this edge. So here is our Hasse diagram of this partially ordered set. And in fact, you can maybe see from this example why less than or equal to is something you would call a linear order. That's a good way of thinking about this name, is that when you draw them in this Hasse diagram way, you will get just a single line. On the other hand, the set 1 through 10 with divisibility, we have seen that this is not a linear order, so I will have a much harder time drawing it. Let's see if I can do the job. So down at the bottom is 1. And what is going to be the next sort of one step up? Since we're doing divisibility, it's going to be the things that are not divisible by anything but 1, namely prime numbers. So what are the prime numbers 1 to 10? They are 2, 3, oh dear, 5 and 7. And we're going to have edges connecting these because 1 divides 7, and divides 5, and it divides 2, and it divides 3. And how do we get one step more? Well, we take things that are divisible, for example, something that's divisible by 2, and not by anything bigger or smaller, is 4. So 4 is going to be next here with a direct connection from 2. But now we're going to start seeing, so the first difference is that we have multiple things coming off of 1 because we have incomparable elements. The other thing that is different from this other case is that we'll start joining up as well. So for example, 6 is greater than or equal to 3. It is also greater than or equal to 2. So we add both these edges because neither of them could be gotten from the other. Okay, so let me just finish drawing this. We need another edge here for 9. We need another edge here for 8. And we need another thing here for 10. All right, that's not a disaster. Here is the Hasse diagram of this set of integers 1 through 10 with partial order given by divisibility. And you can see this is emphatically not a linear order. So here is a way of describing the Hasse diagram more rigorously, which will connect it to the things we were talking about last time more precisely. Say an element y covers an element x. If it's basically the situation where we're drawing an edge in the Hasse diagram, which is to say, if x is strictly less than y, and there's nothing in between, meaning there is no z with x less than z less than y. So the Hasse diagram should contain a line from x to y exactly when y covers x. So for example, this is saying that 6 covers 3, and that is true because 3 divides 6, and there is no number that is strictly between 3 and 6 in this divisibility. So define the covering relation of a partial order to be the relation x comma y, where y covers x. So this this will no longer be a partial order in general, because it will no longer be transitive. This requiring there's nothing in between will destroy the transitive property, but it will still give us a relation. And the covering relation is essentially the data of the Hasse diagram, because we said that we draw a line in the Hasse diagram exactly when y covers x. And one of the benefits of thinking about it in these terms is that then the original partial order is the reflexive transitive closure of the covering relation. And the significance of this is that it's telling us essentially that we can recover the whole partial order from the Hasse diagram. So again, essentially what this is saying is that the Hasse diagram is what we get when we draw a picture of this partial order with only the covering relations. So we're drawing a picture essentially of the covering relation. But saying that it's the reflexive transitive closure, like saying that the reflexive transitive closure gives us back the partial order, amounts to saying that there is a deterministic way to get the full partial order from just the Hasse diagram. So it is a nice, simple way of drawing a partial order that sort of loses no information. and still tells you everything you need to know.